It says, prove that if G and H are cyclic groups of the same order, then G is isomorphic to H. How do we approach this question? From the last video, we spoke about cyclic groups, and we know that every cyclic group has generator. A group is called cyclic if it has a generator, right? So now that's what I started with. Let G in G and H in H be generators of G and H respectively. So we know that the big G, that is the entire group, can be expressed as this, and H can be expressed as this, which is that the set, this G is the set of all the powers of this G right here. And H, also this small h, can generate every other element in it. Another thing that they told us in the question is that G and H have the same order. What is order? Order is the number of elements that is in a group. So that makes us know that the order of G, which is this, represents order like this, is equal to the order of H, and which is also equal to N, where N is the order. Now for these next two lines, we said G is the set of 1, G raised to power 1, G raised to power 2, all the way to G raised to power N minus 1. And H as well is 1, is the set of 1, H raised to power 1, H raised to power 2, all the way to H raised to power N minus 1. Why do we have this? We have this because we know that it's a cyclic group, which means every element in it is a power of the generator that we chose earlier. And the last term would always be the power of the order minus 1, G raised to power the order minus 1. That is the generator raised to power the order minus 1. Since we have defined the order to be N, we can express G and H like this respectively. So the next thing that we do, since we are trying to prove isomorphism, is that we are going to define a map. So we define the map phi as G maps to H to be phi of G raised to power I is equal to H raised to power I, for I being 0, 1, 2, 3, 4, 5, 6, all the way to N minus 1. This should be N minus 1 because the last I here is N minus 1. So to show isomorphism, this is where you need to understand what isomorphism is. Isomorphism has three conditions mainly, which is that if phi is an isomorphism, it has to first be a homomorphism, then it has to be 1-to-1, and then it has to be onto. So these are the conditions that phi has to satisfy for it to be an isomorphism. And we are doing isomorphism because they say we are showing that G is isomorphic to H. So I'm going to clean what's on the board and then show all of this proof to see if it's true.